We are now going to introduce our third magnetic field, magnetization. We know that currents cause magnetic fields. The currents we've been looking at up to now we will refer to as free currents. In materials, we'll have what we will call bound currents, and these bound currents will also generate magnetic fields. An electron in an orbit in an atom is a bound current. So this bound current will generate a magnetic field. You also know that electrons have spin, and we can think of that spin as a current. So the electron will have a magnetic field due to its spin. We can model the resulting magnetic field due to all the electrons going around in orbits and the electron spin as a magnetic dipole moment. So this current will represent the sum of all the bound currents from the electrons going around in orbits and the spin of all the electrons. So we have some area here, S, bounded by our bound current I sub B. So the magnetic dipole moment for each individual atom will be this bound current times the surface area, and the direction will be determined by the right-hand rule, the fingers of your right hand and the direction of the bound current, your right thumb pointing in the direction of the magnetic dipole moment, designated by this unit vector A sub n. If we place this atom in a magnetic field, it's going to experience a torque given by M cross B. So here we have a material, and each individual atom has a magnetic dipole moment associated with it, and at this point they're all randomly oriented, so there's no net magnetic field coming from the material. But now let's place this material inside a magnetic field. The torque these atoms will experience will result in them being aligned along the applied magnetic field, and so now there's an additional magnetic field coming from the material to add to the external magnetic field. This cylinder is some material that contains atoms, and each one of these circles represents the magnetic dipole moment from each individual atom. And the atoms have all been torqued, so their magnetic dipole moments are all pointing in the same direction. So the arrows indicate the direction of the bound currents. And notice internally, any two adjacent atoms have their bound currents going in opposite directions, so those internal bound currents will cancel. The atoms on the outer perimeter, though, will not have an adjacent atom to cancel the current, so you can think of the bound currents as just flowing around the perimeter of the material. So here's the view of the bound currents going around our cylinder. So N is the number of layers of atoms inside this cylinder, so N is the number of bound currents going around the cylinder. When we were looking at electric fields, we saw that free charge generated electric flux density fields. In materials, we had bound charges in the form of those electric dipoles. They led to the polarization field, and we treated the electric field intensity as coming from both free and bound charges. We're going to do something similar with magnetic fields. We're going to treat the magnetic field intensity as coming from free currents. These bound currents in materials will generate a new magnetic field, the magnetization. And magnetic flux density will be due to both free and bound currents. Again, we're seeing similarities between electric fields and magnetic fields, but also differences. Free charge is leading to a flux density, whereas free currents is leading to a magnetic field intensity. To understand the magnetic fields coming from these bound currents, let's first look at what magnetic fields would be coming from similar free currents. The similar free current situation would be one you encounter in a coil or solenoid. We know that if we have a wire with a current flowing through it, that current will generate magnetic flux density fields in the form of circles around that wire. Let's imagine taking this wire and forming a loosely wound coil from it. So if you're close to the wire, the magnetic fields will still be circles. Between the wires, they're going to cancel. And notice everywhere inside, the fields from all the pieces, all the IDLs, are going to be pointing in the same direction and reinforcing. So we'll have a strong field inside. And we know the magnetic flux density field lines always close on themselves. So these magnetic flux density field lines that are coming out of the right-hand side of the coil have to loop around and come back in the left-hand side. So we know that the field outside will be much weaker than the field inside. Here we see the magnetic fields generated by two different coils using iron filings. For this short length coil, you can see the strong field inside and how the field lines quickly fringe out as they have to loop back around, and the field gets weak outside the coil. Here, as we make the coil longer, you can see the field inside, and it starts to fringe out, and very quickly you have a field that's so weak it cannot orient the iron filings. The more tightly we wind this coil and the longer it is, the weaker the field will be outside the coil relative to the field inside the coil. Here is that tightly wound solenoid, and we're looking at a cross-section through the solenoid. The length of the solenoid will be L, and we'll have N turns of the wire. We're going to apply Ampere's circuit law to determine the magnetic field intensity, and this dashed line will be our Amperian loop. It will go down the inside of the coil and then out and around the outside and back in. Down the center of the coil, the magnetic field intensity is fairly uniform, although we'll get fringing of the field outside as the field has to come out and loop back around and come back in the other side of the coil. So ignoring the fringing along this first distance L, we have H inside times L. Now, on these two sides of our Amperian loop, the distance is small, so there won't be much contribution. Plus, essentially, dl is perpendicular to h along most of this path, so h dot dl is going to be close to 0. So we can ignore contributions from these two short sides. Now, the field everywhere outside is going to be weak because these fields coming out of the solenoid have to fringe out quite a bit to loop around and come back inside the coil. So H dot dl along this side we're going to assume is negligible compared to H dot dl inside the coil. So our approximation to the integral of H dot dl around our Amperian loop will be H inside times L. And this approximation will get better and better the longer your solenoid is. Now we have to determine the current enclosed by our Amperian loop. So putting the fingers of your right hand in the direction of our Amperian loop integration, your right thumb points out of the page. So we want to know the current coming out through the surface of the page through this area. Our wire punctures this surface n times. And the current flowing through the wire each time it punctures this surface is up out of the page. So the current enclosed is the number of turns we have, N, times the current flowing in our coil, I. Solving for H inside, we obtain the magnetic field intensity inside the coil is Ni over L, and outside we're going to approximate it as 0. The longer the coil, the better this approximation, and in the case of an infinitely long coil, this will be a perfect approximation because the field inside the coil never comes out to loop back around. In our material, we had n layers of bound current going around our cylindrical material. In our solenoid, we just saw that if we have n turns with the current I going through it with the length L, the magnetic field intensity inside the solenoid was Ni over L. Now we have n layers of bound current, so in analogy, the magnetization M will equal the number of layers we have times the bound current divided by the length of our sample. So the units of magnetization will be amps over meters, just like the magnetic field intensity. So the volume of each atom will be the spacing between the atoms, which we'll call delta L, times the cross-sectional area, which is this area in our magnetic dipole moment, S. We will use a lowercase n to represent the atomic density, the number of atoms we have per cubic meter, and that will be just 1 over the volume of each atom, or 1 over delta L times S. So I've rewritten this equation for the magnetization over here, that M is equal to N times the bound current divided by the length of the sample. The length divided by the number of layers of atoms we have is the spacing between the atoms. So N over L can be replaced with delta L in the denominator. And delta L can be replaced with 1 over N times S. So we can rewrite the magnetization as N times our bound current times S. I sub B times S is just the value of the magnetic dipole moment of each atom. So the magnitude of the magnetization is just N times M, the atomic density times the magnetic dipole moment of each atom. So the direction of the magnetization will be in the direction of the magnetic dipole moment. So magnetization is the product of the density of the atoms times the magnetic dipole moment of each atom. So N is the number of atoms per unit volume. M is the magnetic dipole moment per atom. So the magnetization is the magnetic dipole moment per unit volume. Since the magnetization is magnetic dipole moment per unit volume, you only have a magnetization where you have magnetic dipole moments. So magnetization only occurs within a material. So magnetic dipole moment is a current times an area, amps meters squared. Volume is meter cubed. So again, the units of magnetization are amps per meter. So free currents generate magnetic field intensity, and we saw the relationship between magnetic field intensity and magnetic flux density field was B is equal to mu 0 times H. We're going to associate bound currents with generating magnetization, and magnetization will similarly generate magnetic flux density field, so B is equal to mu 0 times M. So the magnetic flux density field will be that due to free currents plus that due to bound currents. So the magnetic flux density field is equal to the permeability of free space times the sum of the magnetic field intensity plus the magnetization. This is a general expression that holds in any situation for any material.